All right, welcome back everyone to the deep dive. You know how it is, folks. We take a mountain of research, a whole pile of content, and we extract the good stuff for you. What's really worth paying attention to? Well, this time we're looking at text embeddings.
Text embeddings, yeah.
And you might have heard that term before. It's been buzzing around for a while now. And essentially, it's kind of like how we're teaching computers to understand the meaning behind our words in code.
Absolutely.
We turn these words in this code into this like really rich numerical
Yeah.
representation. Think vectors. These vectors are really where it's at. They're like the backbone of all these tasks that we need computers to do. So automatically categorizing documents, finding, the text that's related to a particular topic, organizing just massive amounts of information, even giving you those recommendations you see online.
Exactly. Really, so much of what we rely on in our digital lives is powered by text embeddings in one way or another. And the thing is, this whole field is constantly evolving.
Right.
Like every other area of AI these days, it feels like there's always something new and exciting emerging. And so today we're going to take a deep dive into one of the latest developments, something called Gemini Embedding.
Exactly.
Catchy name, right?
Yeah.
So our main source material for this deep dive is going to be the research paper Gemini Embedding, Generalizable Embeddings from Gemini, which was pretty recently released.
Just came out.
Yeah, fresh off the press, as they say.
Yeah.
So what we really want to do today is try to, unpack Gemini Embedding. What is it? What's all the fuss about?
Why are people so excited about it?
Exactly. And more importantly, what sets it apart?
Yeah.
We're going to especially focus on some of the more academic aspects of it, like the architecture of the model and how they actually go about training it.
Okay.
So, ready to dive in?
Let's get into it. I mean, right off the bat, the name itself kind of gives us a hint that it's built on something pretty substantial, right?
Right, you're absolutely spot on. I mean, the name basically screams it out, doesn't it? Gemini Embedding.
Yeah.
It's built on Google's most powerful and versatile large language model, Gemini.
Gemini. Okay, so we're talking about the same Gemini that's been making waves with its ability to not only handle text, but also images and audio.
One model to rule them all. That's the goal, at least.
So how does tapping into a model like that, so powerful and versatile, how does that give Gemini embedding this head start in the race to create these really good text and code representations?
Okay, think about it this way.
Okay.
Gemini itself has already gone through an insane amount of pre-training.
Right.
It's been fed a ridiculous amount of data, a truly massive and diverse data set. So it's absorbed so much about the complexities of language, even the structures and patterns you find in code.
Wow.
By initializing the embedding model with all those parameters, all that learned knowledge from Gemini, Gemini embedding kind of starts the race miles ahead of the competition.
Interesting.
It already has this deep understanding of semantics, the relationships between different pieces of text, the underlying patterns in code.
Right.
It's as if the model has already done like a whole PhD in linguistics before even starting on its specific embedding task.
It's like, yeah, it's got all this background knowledge. It's like a student who's already done like a whole liberal arts education.
Right, exactly. A broad foundation.
And now they're just focusing on like, that specific major.
Exactly.
All right, so we have this incredibly powerful base in Gemini. Now, I want to get into the nuts and bolts. How does Gemini embedding actually create these embeddings from a piece of text or a chunk of code?
Sure.
Like, what's the step-by-step process? What happens as it goes through the model architecture?
All right, let's break it down. We start with an input sequence of tokens, right?
Tokens.
So these are the fundamental building blocks. Think of them as individual words or even parts of words. The research paper, they use the letter T to represent this sequence.
Okay, T for tokens.
Exactly. So this sequence, T, it gets fed into the model, which they represent as M.
M for model.
You got it. Now, M isn't just any old neural network. It's what's called a transformer architecture.
Okay.
It's this type of neural network that's really good at understanding context and relationships in sequential data, which is exactly what we need here. And critically, this transformer, M, it's initialized with those pre-trained weights and biases that we were just talking about, the ones from Gemini. This whole process spits out a sequence of token embeddings. The researchers, they call this TEMD.
TEMD.
Yeah. And if we want to get all mathematical about it, if the input sequence has a length of L and the model has an internal dimension, let's call that 8M, then TEMD exists in this high dimensional space, kind of hard to visualize, but they represent it as OM. So basically, each token in the input now has this rich vector representation that captures its meaning, but importantly, it's within the context of the entire sequence.
So what you're saying is at this point, we've got a detailed vector for every single piece of our input, whether it's text or code.
That's the idea.
But for a lot of real-world applications, things like classifying a whole article or figuring out how similar two code snippets are, you need a single embedding that represents the whole thing, right?
Right.
Not just all the individual pieces. So how does Gemini Embedding take this sequence of embeddings, all those tembeds, and boil them down into one unified representation?
Okay, good question. And that's where this thing called the pooling mechanism comes in. They call this P. So P takes this sequence of token embeddings, the tend, which remember is in that A char M space, and it squishes them all together into a single fixed size embedding vector. They call this pembed. And pemmed is still in that same high dimensional space, say char M. The paper specifically mentions that they use what's called mean pooling.
Mean pooling.
Yeah, it's pretty straightforward, actually.
Okay.
They just calculate the average of all the token embeddings.
Average.
Yep.
Just straightforward average.
Element-wise average, to be precise. So for each of those OM dimensions, they take the average value across all L tokens.
Interesting. So it's simple but often effective. Kind of a theme we see in a lot of, really solid engineering, isn't it?
Absolutely. Less is more sometimes.
Okay, so we've gone from a bunch of individual token representations to a single average representation of the whole input. Is this PEMmed? Is this the final embedding that gets used for the downstream tasks?
Almost there, but not quite. There's one last crucial step. It involves a linear projection, and they represent that with the function f. This projection takes that pemmed, which remember is in LME, and it maps it to the target embedding dimension. We'll call that out. So the output is our final embedding, E, and it exists in the space euro.
Okay.
Now get this. The paper explicitly states that for Gemini embedding, the output dimension, O, is a whopping 3,072.
3,072 dimensions. That is a lot. I mean, that really tells you that this embedding has a huge capacity to encode a lot of subtle nuances and semantic information, right?
It can hold a lot of meaning, that's for sure.
Okay, so just to recap the whole architecture journey, we start with our text or code as a sequence of tokens, T. This gets processed by the Gemini initialized transformer, M, to give us those token embeddings, temmed. Those get averaged using the pooling mechanism, P, to produce pemmed. And finally, that linear projection, F, scales it to the final 3072 dimensional embedding, E.
You got it. Nail it.
Okay, I think I'm following. Now, the really interesting part, how does this whole architecture actually learn?
Right.
How does it learn to generate these embeddings that really capture the meaning and the relationships within the data? What's the goal?
So the goal at the highest level is to teach the model to distinguish between related and unrelated pieces of text and code, but in the embedding space.
Okay.
So they use a technique called noise contraptive estimation. Usually people just call it NCE. And it relies heavily on what are called in-batch negatives.
In-batch negatives. All right, that sounds important. Let's break down what exactly makes up a training example in this learning process.
Okay, sure.
What are we actually feeding the model?
So a typical training example has several components. First, you have a query. They use FUA to denote this. This could be anything, really, a search query, a question, a snippet of code.
Right.
Then you have a positive target.
Okay.
That's YEG, plus it's a piece of text or code that's semantically related to the query. So for example, if the query is a question, the positive target would be the answer to that question.
Makes sense.
Now, you can also optionally include a hard negative target, and they call that YE.
Hard negative.
This one is a piece of text or code that might look related to the query on the surface, but actually isn't a correct match.
Tricky.
Yeah, it's like a deliberate challenge. It forces the model to really learn how to discriminate.
I see.
And lastly, each training example has a task string. They use OAK for this.
Yeah, for task.
Exactly. It could be something like question answering, code search, document retrieval. This string gives the model context. It tells it what specific task it should be learning to perform embeddings for.
So basically, we're giving the model a bunch of labeled examples, like flashcards almost, right?
Right.
And these flashcards are saying, hey, these pairs, query target, those should be close together in the embedding space. And these other pairs, query negative target, those should be far apart.
You got it. You're teaching the model what's similar and what's different.
Okay, so both the query and the target passage, whether it's positive or negative, they both go through that whole model architecture that we just talked about, right? The Gemini initialized transformer, the mean pooling, the linear projection, all that.
Exactly. And out pops their respective embedding vectors in that 3072 dimensional space, OU.
Okay.
Equation 1 in the paper actually spells out this embedding process formally. It looks like this. Q equals Fi mean pool in Cardi U. You'll notice they're using this task prompt that gets added to the query before it goes into the model. This is how they explicitly tell the model what the intended use of the embedding is.
So it's not just the raw text or code, it's also getting this extra signal about what the embedding is going to be used for.
Right. Context is everything.
Makes sense. It's like giving the model extra clues to help it learn. All right, now let's get to the core of this learning process. The loss function. This is where the model actually gets feedback on its performance, right? It learns from its mistakes.
Exactly. The loss function is like a scorecard. It quantifies how well the model is doing, and more importantly, it guides the learning process. So here's what the equation lives with. You ready for this?
Hit me with it.
L equals 1x e 282999 a log osim plus orsim plus esim plus osim plus osim plus o asim plus a20 pass sim cos a esim plus o plus osim plus asim plus o osim plus a20 and a20 by 99 log. It's basically a measure of how similar the direction of those two vectors is. It ranges from -1, which means they're pointing in completely opposite directions, to 1, meaning they're pointing in the exact same direction. 0 means they're orthogonal.
Okay, so the closer to 1, the more similar they are.
Exactly. And then you have this mask u term, which is defined in equation 3 as mask u is 0 if cree or u plus u equals otherwise.
Okay, I see. It's making sure that the model isn't accidentally comparing a query to itself or its own positive target when it's calculating the loss.
You got it. They're trying to avoid any sort of self-comparison, which could mess up the learning.
Makes sense. So looking at this whole equation, it seems like for each query in the batch, the model is trying to boost the score of the positive target.
Right.
And the cosine similarity is the metric it uses for scoring.
Exactly.
And that logarithm part ensures that there's a larger penalty when the similarity between the query and the positive target is low, or when the similarity between the query and other negative targets in the batch is high.
You're getting it. The model is trying to minimize the overall loss across all the training examples. The lower the loss, the better it's doing.
It's all about reducing that loss. Okay. Now, the paper mentions that they specifically don't use something called same tower negatives.
Right, good catch.
Which other embedding models, like Gecko, have used?
Yeah.
So first off, what are same tower negatives?
So imagine you take a positive target and you tweak it a bit, maybe change a few words, create some variations, and then you feed that modified version through the same embedding model.
Uh-huh.
And you get another representation. That's new representation. That's your same tower negative. It's considered a negative example for the original query.
Interesting. And why did the Gemini embedding folks decide against using those?
Well, what they found is that adding these same tower negatives actually made the performance worse on most of the tasks they tested.
Really?
Yeah, they think it's because these tweaks might actually create what are called false negatives. So you have examples that are still semantically related to the original query,
Okay.
but because of the way they've been modified, they get flagged as negative, even though they're not truly negative.
So it's like introducing noise into the training data.
Exactly. It confuses the model. It makes it harder to learn those really robust semantic relationships that we're after.
So it seems like they're prioritizing the quality of those negative examples, making sure they're really good, even if it means having fewer of them in certain situations.
Exactly. Quality over quantity.
Makes sense. Okay. Now there's another term that pops up in the paper, Matryoshka representation learning. They call it MRL.
MRL.
Sounds kind of cool. What's the role of that in Gemini embedding?
So MRL, it's a pretty clever trick.
Okay.
It lets a single model output embeddings at different dimensions. So you can get embeddings all the way from a smaller size, like, 768 dimensions, up to the full 3072.
Oh, that's interesting. So you can scale it up or down depending on what you need.
Exactly. It's about flexibility. And the way it works is that the loss function is designed to operate on overlapping parts of the final embedding vector. So during training, part of the loss might focus on the first 768 dimensions, another part on the first 1536 dimensions, and then another on the whole 3072.
So they're training it on like different segments of the embedding simultaneously.
Exactly. They make the training objectives hierarchical. The beauty of this is that once the model's trained, you can choose which dimension you want to use.
Right.
So if your application is limited by memory or processing power, you can use a lower dimensional embedding, and it'll still work well because the model's been trained on the full thing.
That's really cool. It's like getting multiple models in one.
Precisely.
All right, we've covered the architecture, the training objectives. Now let's talk about how this model is actually trained in practice. The paper describes a two-stage process.
Right.
What are these stages? What's their purpose?
Okay, so the training of Gemini embedding involves two key stages, pre-fine-tuning and then fine-tuning.
Pre-fine-tuning and fine-tuning. Okay, so what happens in pre-fine-tuning? What are they trying to achieve there, and what kind of data do they use?
So the main goal of pre-fine-tuning is to take the model, which initially was all about predicting the next word in a sequence that's called autoregressive generation.
Okay,
And they adapt it to the task of encoding, which is creating these dense, fixed-size representations of whole sequences.
right.
This stage involves training on a massive amount of data, tons of query target pairs, and a lot of this data might be a little noisy. It doesn't have to be perfect at this stage. And importantly, during pre-fine-tuning, they don't use that hard negative term, the ou, in the loss function.
Interesting. Why not include those hard negatives right from the start?
Well, they're focusing on the bigger picture first. They're shifting the model's focus from generation to this discriminative embedding task. They use a really large batch size in this stage,
Okay.
which helps stabilize the training process, and the model can learn to handle some of that noise that might be present in the data. They found that giving the model this broad exposure to a ton of relational data, even if it's not perfectly clean, it's more beneficial for this initial adaptation than focusing on really fine-grained discrimination with hard negatives right away.
So it's about building a solid foundation before moving on to the more nuanced learning.
Exactly.
And how long does this pre-fine-tuning go on for?
Well, they typically train for many more steps during this pre-fine-tuning phase than in the later fine-tuning stage. It's about laying down those neural pathways, getting those connections firing.
So pre-fine-tuning is all about teaching the model the basics of encoding, giving it a general understanding of how to represent text and code in this dense vector space.
Exactly.
Okay, and then we move to the fine-tuning stage.
Right.
What's the focus in this stage, and how does it differ from pre-fine-tuning?
Okay, so in fine-tuning, they really fine-tune the model's understanding.
Makes sense.
They optimize it for a whole bunch of specific tasks.
Okay.
They use a carefully curated mix of task-specific datasets, often with human annotations. And in contrast to pre-fine-tuning, this stage does include those query target, hard negative target triples, both in the data and in the loss function.
So now they're bringing in those challenging negative examples of really pushing the model to make those subtle distinctions.
Ex-
Are there any other key differences between fine-tuning and pre-fine-tuning?
Yes, during fine-tuning, they use smaller batch sizes, typically less than 1024,
Okay,
and they often limit each training batch to examples from a single dataset.
I see.
This way, the model gets a much stronger learning signal for that specific task.
It's like focusing its attention on one task at a time.
Right. So, for example, if it's working on a question answering data set, it learns to pick out the correct answer from a bunch of plausible but incorrect answers.
Okay.
They also do a grid search over various training hyperparameters during this stage.
Hyperparameter tuning.
Yeah, to find the best possible configuration for maximizing performance across all the target tasks.
So they're really optimizing everything, fine-tuning those knobs and dials to get the best possible results.
Exactly.
Now, there's one more technique that they mentioned in their training recipe, and it caught my eye. Model soup.
Model soup, yes.
What's that all about, and how does it contribute to the final Gemini embedding model?
Okay, so model soup, it's actually a pretty straightforward concept. It's about taking multiple independently trained models,
Okay.
and then you just average their parameters together, the weights and biases.
Average them together.
Yeah, the idea is that by combining the different perspectives that each of these models have learned, you get a final souped model that performs even better on unseen data. It's more robust to variations in the input.
It's like taking a bunch of experts who've all studied the same subject, but have slightly different approaches. And you're blending their knowledge together.
Exactly, you're creating like a super expert.
Right. So how do they decide which models to combine in this soup?
They experimented with a bunch of strategies, sometimes averaging checkpoints from the same training run,
Okay.
sometimes averaging models from totally separate training runs, and sometimes even using weighted averages where some models contribute more than others. They chose the final set of models based on a few factors, like how diverse the data they were trained on was, and
Okay.
how well they each performed on a development set of tasks.
So it's not just randomly throwing models into the pot. There's a method to the madness.
There's a science to it.
Right. That's fascinating. So they're using this model soup technique to potentially squeeze out even more performance without having to do any extra work during inference.
Exactly. It's like a free performance boost.
All right. So we've covered the foundational model, the architecture, the training objectives, that two-stage training process, and even this model soup thing. Now, something that really stood out to me in the paper is how much emphasis they put on improving the quality of the training data itself.
Right. The data is key.
And they use Gemini for this, which I thought was really interesting. So how exactly are they using Gemini in this data curation process?
Okay, so this is one of the most innovative parts of their research. They use Gemini's language understanding and generation capabilities to improve the quality of their training dataset in three main ways: generating synthetic data, filtering existing data, and mining for hard negative examples.
Okay, so let's start with synthetic data generation. How are they using Gemini to create brand new training examples?
They build on some previous research in this area and use a technique called few-shot prompting.
Okay, few shot prompting.
You give Gemini a small number of carefully chosen examples,
Okay,
and this guides its generation process. For retrieval tasks, for example, they prompted Gemini to come up with synthetic search queries for existing web pages.
interesting.
The goal was to expand their training data with a wider variety of queries that users might actually search for.
So they're using Gemini to simulate like real world search behavior.
Exactly. And then, to make sure the quality is good, they use another Gemini-powered tool, an auto rater. So they ask Gemini to evaluate the quality of these generated query passage pairs, looking at relevance, coherence, stuff like that.
So they're having Gemini check its own work.
Exactly. Any low-quality examples, anything that looks unrealistic or doesn't make sense, those get filtered out.
I see. And what about classification tasks? How do they use Gemini to create synthetic data for those?
For classification, they get a bit fancy.
Okay.
They use what are called multi-stage prompting strategies to create data sets for sentiment analysis, review classification, things like that, mostly in English.
Okay.
They might condition the generation on synthetic user profiles, product descriptions, or even movie synopses.
Wow.
So the generated data is more realistic and grounded in a real-world context.
So it's not just learning from the data, it's actually helping create and refine the data it learns from.
It's a feedback loop.
That's pretty wild. Okay, what about data filtering? How are they using Gemini to clean up existing data sets that have already been annotated by humans?
So even in data sets that have been labeled by humans, there can be mistakes,
Right.
incorrect pairings.
Yeah.
To deal with this, they use Gemini with few-shot prompting, but this time it's about assessing the quality of the data.
Okay.
They ask Gemini to look at a query positive target pair or a query negative target pair and determine if it makes sense semantically. Based on what Gemini says, they can then remove any examples that are potentially problematic.
So it's like having an AI assistant that's super good at proofreading.
Exactly. And this is really crucial because if the data is bad, the model will learn the wrong things.
Right. Garbage in, garbage out.
Exactly. Okay, and then there's the hard negative mining.
Yeah, we talked about how important those challenging negative examples are earlier. So how does Gemini help with finding them?
All right, their hard negative mining approach, it's a multi-stage process. And again, they use Gemini's understanding of semantic similarity.
Okay.
They start by training an initial version of the model, but they don't use any explicit hard negatives in this initial training.
Okay.
Then, for each query in the dataset, they use this initial model to find the nearest neighbors in the embedding space.
Right. So these are the data points that the model thinks are most similar to the query.
Exactly, and those become the candidates for hard negatives.
Right. Because they're similar to the query, but they might not actually be a good match.
Right, so here's the key step. They then use Gemini to score these nearest neighbors in relation to the original query.
Okay. How do they do that?
They use two different prompting strategies: graded classification, which means asking Gemini to rate how related the retrieved passage is on a scale.
Okay.
And then query likelihood, which is asking Gemini how likely it is that the retrieved passage would be a relevant result for that query.
Ah, so they're getting Gemini's opinion on how good of a match it is.
Precisely. And they combine these scores using something called reciprocal rank fusion, or RRF. And the neighbors with the lowest combined scores from Gemini, those become the high quality hard negatives for the next training stage.
So they're using a preliminary version of their model and Gemini's understanding of language to pinpoint the most challenging negative examples.
Exactly. It's a really sophisticated way of refining the training data.
It's really impressive how much they're using Gemini throughout the entire process. Okay, so after all this work, all this careful design, training, data refinement, how do they actually evaluate how well Gemini embedding performs?
They conduct a very thorough evaluation
Okay.
across a wide variety of tasks and languages, but they mainly focus on this benchmark called the Massive Multilingual Text Embedding Benchmark.
That's a mouthful.
It is. They just call it MMTT.
MTB. Okay.
This benchmark is incredibly comprehensive. Over 100 different tasks, spanning over 250 languages and 10 different types of tasks.
Wow.
They test things like bytext mining, so finding parallel sentences in different languages,
Okay.
text classification, semantic clustering, document and code retrieval, and measuring semantic textual similarity.
So they're really putting it through the paces.
Oh, yeah. They specifically report their performance on 3 subsets: MTIB, multilingual, MT-Kang, V2, and MTB.
250 languages. That really highlights how generalizable Gemini embedding is.
Absolutely. It's designed to work across a wide range of languages, not just 1 or 2.
Okay, so what were the standout results on these MT benchmarks?
So on the MTB multilingual benchmark, they achieved state-of-the-art performance. They hit a task mean score of 68.32.
Okay.
That's a huge jump, an improvement of plus 5.09 over the previous best model.
Wow, plus 5.09. That's a significant improvement.
It is. They also achieved the highest task type mean of 59.64, which is a plus 3.64 increase over the previous best.
Okay.
That means they're performing really well across all those different categories of tasks.
Right. Not just good at one specific thing.
Right. And on top of all that, they secured the top spot on the public MTB leaderboard based on the border rank.
So they're number one. That's a really impressive improvement in overall multilingual embedding performance. And they didn't just focus on multilingual tasks, right?
Yep, they tested it on English-specific tasks and code-related tasks as well. They wanted to see how well it generalizes across different domains.
Right. So it's not just a one-trick pony.